IBM Advanced Data Science Specialization via Coursera. My use case is part of the larger natural language processing project known as the sign language recognition. Sign language is a means by which impaired hearing individuals or community communicate with one another. It involves the use of gestures as well as the facial expression. Like a spoken language, linguistics considered sign language as a natural language of its own, with its own set of grammars and lexicons. It varies from country to country and evolves over times. So the main idea of our sign language recognition project is to have a language recognition system that can serve as a translator between the sign language speakers and the spoken language. And this can come in the form of text, voice, or both. Sign language is mainly used by a deaf community. However, hearing individual with inability to physically speak also use sign language to communicate. More so, people with spoken language challenges, which could be due to disability or other condition, also use sign language to communicate. And relatives and friends of the deaf individual also use sign language to communicate with individual. My use case data set is obtained from the Open Data project, and it exists in two versions. The pre-processed version, which is available in Kaggle, it is the sign language digits images, while the original image exists in GitHub page. It is a sign language digits which is donated to the Open Data project by a high school student in Ankara, Turkey. It is an image of 100 by 100 physics with RGB color and consists of 10 classes from 0 to 9. About 218 students participated in the project. On average, each student supplied 10 samples. This dataset is useful for a proof of concept. So my use case is sign language digit classification. It is a classification task, a supervised classification machine learning task, and it intends to train a machine learning model that translates a signed digit image to their equivalent numeric value. So to implement this, we use Jupyter Notebook on IBM Watson Analytic environments. This takes care of the GPU scaling automatically, and using Keras on top of the TensorFlow as a deep learning framework for this project. And lastly, the final reports of the solution is generated based on the Jupyter Notebook implementation. Since the main idea of the sign language recognition is to have a system that translates signed images into its corresponding numeric value, a sequential model based on multi-layer perceptron framework was the preferred choice of machine learning architectures. And this model has a proven performance record in the related image classification tasks. So that data set exists as in the file formats. It exists in the file formats and file and subfolder forms, and each file and subfolder, each subfolder is labeled according to the images it contains. Let's see the initial exploration. So in the project, I used the second version, which is the original images, and the reason is that the first image, which is the first version of the data set, which exists in Kaggle as a pre-processed NumPy image array, during the initial exploration, I realized that there are some discrepancy in the mapping between the image and the corresponding numeric value. So for this reason, I decided to use the original image and pre-process it in my own terms. So the data set exists as in a folder format. Each subfolder is labeled according to the image it contains. A subfolder 0 contains image of signed digit image of 0. Subfolder 1 contains signed image of 1 in the in that order. So for the initial exploration, we use some of the we import some of the packages and modules that are useful, like OS, which is useful in accessing a specific location of the files. The numpy array and the pl are used for presentation of the images, and then the matplotlib, which is used in display of the image in the output of Python output, or through the visualization, which will, in this case, we visualize it with the histogram. So these are the image. After the extracting of the image, let's assume the first image. Here we are using the matplotlib to visualize the image. You can see the image is what's here. We have I think should be 3, which is the first image, which is 0. When you take any image, let's say image number 10, that's 11. In this case, you can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 8. So let's see the actual image here based on the 8 is this. So you can see I think here that is 8. So in that order, so we can visualize to ensure that the target numeric values coincide with the actual image we are seeing. So here we try to see the view of the visit value of the image as well as the histogram on to visualize it, how skew it is. So since this is an offline processing task, the initial data sets which exist in folder and subfolder formats labeled according to the digit it contains, each subfolder contains. The original data is zipped and uploads onto the IBM Apache Spark Cloud object storage in this zip folder. So to process the data sets using IO modules with Pythons, we extract the classes. Oops. What goes wrong? File not zip for. Oh, I think I've not. Okay. Okay. I think did I do this? Maybe I didn't run this. Yeah. Now we extracted this. So this is used to we extract the classes from 0 to 9, and then the extraction of the data sets. Here we use Keras pre-processing image generator, data generators, which generate a TensorFlow images. We are extracting the batches in batches. Here we define the training part. The target size is we reshape it to 64 from 100 by 100 pieces to 64 by 64, and it contains the class required, and the batch size is the size of the training assessment before. So we run this. Yeah, about 1238 images belonging to 10 classes. So the same for validation as well as the tests. So here we can see after having the batches, we have to extract the next training batches in that order. Well, here we are doing it one time. This for the test training, validation, and the test. Yep. So we can kind of visualize any of these specifically. Yeah, I think okay, we can take this. Let's see. just to visualize using matplots. Okay, visualize a file using matplots to see. So we have done that before. So the first here is this is 4, I presumed. What about the same? Yeah, let's see the corresponding. Yeah, it's 4. So just this for visualization, and this completes the process for extraction, transformation, and load of the data. Next, we look at the features engineering, which is also here we try to present the images in the format that is acceptable by our the chosen machine learning model, which is in this case is a sequential model. Uh, how our data deep learning framework, which is Keras, will obtain these features. So we look at the features engineering. Definition, training, evaluation, and deployment can be explained in one shot. But first, let's see the feature engineering so that we can see how things are. So this is the module for feature engineering. Of course, for each part, we generate the decision guidelines. We document the decision we have taken for each of the processes we go through. Of course, this is just putting on top of the what you have done previously. So the structured files are three-dimensional, which is the image. So, but our sequential model, the Keras framework requires that this image should be flattened into two-dimensional. So to do that, the first aspect of the feature engineering is to flatten the data set into two-dimensional. Here the training is reshaped to two-dimensional, and the validation same way for each size based on the number of the sample it contains. So we flatten them to two-dimensional, and to normalize the values, we divide each values with 255 so that we have the value range from 0 to 1, which is a good practice. Here we apply the one hot encoding to the classes. Now let's go to the final reports, which give us the remaining, since we don't have much time to go through each stage by stage, but we're going to look at the project model deployments, which contains all the previous stages. Then here is the data definition. We define our sequential model, adding dense layers using the activation, reviewers activation, and input shapes defined here, which is only for the first time. We don't need to define it for the rest, just one time. And here we had the drop out of 0.2. Yes, the second dense layer is defined with activation, same thing with the first, and the last dense layer consists of the numeric value classes with the activation softmax, since we are using one hot encoding in this case. So we generate the sequential data definition layers, which is defined here. Here you can see no training parameters for this. So during the model compilation, we define the parameters, the loss function. Here we use the mean square error, and then the optimization. We use we try different optimization, but the post and performance we obtain it using the SGD, which is stochastic gradient descent, by tuning the learning rate. Here is 0.01, and particularly tuning the learning rate and the momentum give us the best boats during the implementation. And for the evaluation, the percentage accuracy as well as the loss function values are used for to compare the performance. So during the training, epoch and batch size somehow influence the performance, but after a little tuning, this was used so far, and the training process took place, and finally the model is generated, which using the model evaluation. Here we use the loss function as well as the percentage performance accuracy in terms of percentage accuracy. So we compare the performance when using the test data, validation data, as well as the train data. This is important to safeguard against the overfitting. So in terms of test, the accuracy was 71.74. So far, this is what I obtained. I know there's room for improvement with the loss function of 0.04. For validation, it's around 76.34, which is somehow very close. But for the train, it's around 99.6. It is clearly somehow overfit. But as I say, this is not a perfect model, and there's room for improvement. After this, then this is just additional. When you have a better result, you need to save the weight so that it can be deployed for usage. So this explains the data pre-processing and features engineering, as well as the deployment of the reports, as I've said earlier.